What does it mean for a star to die, if its light still lingers, if its silence still echoes through the cosmos? Long before humanity built the instruments to read the faint whispers of collapsed suns, astronomers watched the sky with patient wonder. They saw stars flare into brilliance, then fade, as though obeying a script written by the universe itself. But not all obeyed. Some, long past the point of death, continued to shine faintly, their glow stretching beyond the predictions of science. Their survival hinted at a defiance buried deep within the fabric of matter. As telescopes sharpened their gaze, the mystery deepened. White dwarfs, tiny stellar corpses, cooled far slower than the models had promised, their dim embers refusing to vanish. Neutron stars, impossibly dense, beat with rhythmic pulses that carried across the void like the heartbeat of something neither alive nor gone. These pulsars, discovered in 1967 by Jocelyn Bell Bernal, stunned the scientific world. At first, their perfectly timed signals seemed so unlikely, so precise that some whispered of extraterrestrial intelligence. Instead, they revealed the strange endurance of collapsed stars, spinning remnants that defied decay. Supernova remnants, too, carried the same paradox. Clouds of gas expanding outward bore the unmistakable mark of destruction. And yet, at their core, survivors remained, silent, dense, luminous, in ways no one had foreseen. These were the first glimpses of immortality in the heavens. Stars that should have perished, yet persisted, dead, yet not gone. Their existence forced humanity to ask, is death in the universe ever truly final? Or does every ending carry within it the seeds of another form of being? In the grand theater of the cosmos, stars are born with certainty, live with brilliance, and die with inevitability. Their lifespans are measured not in centuries or millennia, but in billions of years, carved into the mathematics of gravity and fusion. The script seems written in the elements themselves. Hydrogen fuses into helium. Helium into heavier atoms until the core can no longer sustain its weight. Collapse follows, violent or quiet, depending on mass. A star becomes either a fading ember or a catastrophic explosion. In this language of physics, death is a certainty as strict as the ticking of a clock. Yet, even the most carefully written scripts can be broken. Astronomers expected white dwarfs, the corpses of medium-sized stars, to cool in orderly silence. The physics was simple, without nuclear fusion. Their only source of heat would be the faint release of stored thermal energy, radiating outward until they faded into darkness. Neutron stars, the remnants of more massive progenitors, were thought to be no different, though dense beyond imagination, cramming the mass of the sun into the space of a city. They, too, were supposed to follow a predictable arc of decline. The cosmos would dim them into obscurity, but the universe did not cooperate. White dwarfs were found still glowing billions of years after models said they should have darkened. Their surfaces, instead of cooling like dying coals, seemed to retain heat, as though some unseen furnace still smoldered inside. The very laws of thermodynamics so trusted in every laboratory on Earth were being bent in the skies above. Neutron stars, too, refused silence. When Jocelyn Bell Bernal recorded the first pulsar in 1967, its clockwork regularity confounded even the most disciplined scientific minds. A dead star should not have the power to sing across light years with such precision. Some thought the signals might be messages from distant civilizations, but the truth was stranger still. A collapsed star, its core crushed to nuclear densities, was spinning with such intensity that its magnetic fields beamed radio pulses toward Earth with the accuracy of an atomic clock. A corpse that should have been silent was instead ringing like a bell. The scientific shock ran deep. If the life cycle of a star could not be trusted, what else in the universe might slip free from its equations? Astrophysicists began to see cracks in their models. Cooling curves failed to match observation. Some neutron stars blazed with X-rays long after their heat should have dissipated. Others showed magnetic fields so strong that they defied the known limits of physics, twisting space itself into violent outbursts. It was as though the dead were not only lingering, they were refusing burial. The laws of nuclear fusion had promised closure. A star, once it exhausted its hydrogen, helium, and heavier elements, should have no fuel left to resist collapse. Its fate was sealed by gravity and entropy. Yet these lingering remnants hinted at secret reserves of energy. Perhaps latent nuclear reactions, perhaps crystallization deep in their cores, releasing heat in ways unimagined. Perhaps exotic particles whispering through their dense interiors, carrying energy where none should flow. For scientists, the tension was profound. The universe had been explained in stages, neat diagrams in textbooks tracing the arc of stellar lives, main sequence, red giant, collapse, death. Yet here were stars that refused the timeline. Lingering in defiance of the order written by theory, their silence was not silence at all, but a deception and illusion that hid mechanisms unknown. The shock was not simply technical, it was philosophical. The cosmos had revealed itself to be untidy, unwilling to fit the molds carved for it. Human intellect sought linearity, beginnings and endings, but the universe unfolded in recursive spirals, in echoes, in defiance. The remnants of stars suggested that death, even here, is not an end, but a transformation, an ambiguity the equations struggled to capture as data accumulated. The unease deepened, supernova remnants glowed with unexpected persistence. Dwarfs pulsed with magnetism long after their cores should have solidified into silence. Neutron stars released bursts of energy so violent they shook the detectors on Earth. Each observation forced physicists to ask the same unsettling question. What if the cosmos does not obey the boundaries we set for it? For centuries, humanity believed the stars to be eternal and changing lights suspended in heaven. Then science revealed their mortality. Now, in the corpses of suns, another revelation arose. Death itself may be more complicated, less final, more resistant than imagined. A universe that once seemed governed by the tidy certainty of equations was, in truth, filled with strangeness, with echoes, with refusals. And so the script of stellar death was no longer a closed book. It was a manuscript with torn pages, margins rewritten by forces unseen. The stars themselves were the editors, refusing to sign the final line. The shock still lingers in science today. Each observation of a star that refuses its fate is a reminder that the cosmos is larger than its models, that even in death, light may linger, sound may echo, energy may stir, and in that refusal lies a profound truth. The universe is not an obedient stage. It is a restless sea, where even the silence of stars carries mysteries not yet spoken. When a star dies, the cosmos does not simply close the curtain. Its remains leave behind whispers, faint echoes that ripple across the void. And as the 20th century deepened into the 21st, humanity built new senses to listen, radio dishes stretching. Like steel flowers across deserts, orbiting telescopes rising beyond the veil of atmosphere, instruments capable of seeing the universe not with eyes, but with wavelengths once hidden. Through these lenses, the silence of collapsed stars revealed itself to be an illusion. Death was not quiet, it was restless. Radio astronomy first caught the pulse. Faint metronomic beat of neutron stars spinning in darkness traveled across interstellar distances with impossible precision. Each rotation flung beams of radiation through space, so stable they rivaled atomic clocks. They were not voices in the human sense, but they were signals, and they told a story. Even in collapse, matter could retain order, rhythm, persistence. These were the pulsars. Discovered in 1967, their regularity so uncanny that scientists briefly labeled them LGM, Little Green Men Be. For physics revealed the truth. They were not aliens, but stellar remnants refusing to fade. X-ray astronomy brought a new layer of revelation. White dwarfs, long assumed to be cooling embers, glowed faintly in high-energy radiation. Some billions of years old, still radiated warmth, unexpected by models. Their cores seemed to crystallize like diamonds the size of Earth, releasing latent heat as they froze, hidden furnace slowing their decline. Others shone with even more enigmatic light, as though unseen processes stirred deep within their density. It was as if collapse had unlocked reservoirs of energy no one had anticipated. Then came the most violent whispers, magnetars. Born from the same crucible as neutron stars, they were something far stranger. Their magnetic fields were trillions of times stronger than Earth's, so intense that atoms themselves twisted under their force. A teaspoon of magnetar matter would weigh billions of tons, yet its field could stretch across light years, cracking the crust of the star in seismic quakes. These eruptions sent bursts of X-rays and gamma rays screaming through the galaxy cosmic sirens, announcing that death had not silenced them, but transformed them into something more dangerous. In 2004, one such flare from a magnetar 30,000 light-years away briefly overwhelmed detectors on Earth, brighter than anything seen in the X-ray sky before. If it had been closer, it could have stripped Earth's atmosphere. A dead star had become a weapon of cosmic proportions. Patterns began to emerge. White dwarfs cooling far too slowly. Neutron stars maintaining heat long after theory demanded. Darkness. Magnetars releasing sudden storms of energy, as if their deaths had left unfinished tensions within their cores. Each observation was a contradiction to the neat symmetry of stellar evolution. Each was a reminder that collapse is not the end of a story, but the beginning of another. The persistence of thermal radiation puzzled astrophysicists. In theory, a white dwarf should cool predictably, its light fading into blackness over billions of years, until it became an invisible Cinderella black dwarf. Yet no black dwarfs have ever been seen. The universe itself is not old enough to contain them. Instead, astronomers watch the slow cooling of these remnants and find irregularities. Some are warmer than they should be. Others glow with unexplained luminescence. Crystallization, magnetic fields, and even dark matter interactions have been proposed as secret furnaces delaying the inevitable fade. Neutron stars posed even deeper riddles. Their heat should vanish quickly, radiating away into the vacuum. But X-ray telescopes revealed many remained inexplicably hot. Some appeared to be reheated by internal reactions. Superfluid particles within their cores releasing energy as they shifted phase. Others hinted at processes beyond known physics, exotic states of matter that could only exist under pressures greater than those inside atomic nuclei. Perhaps quarks roamed freely there, perhaps entirely new forms of matter condensed in their depths, leaking energy into the vacuum around them. And then there were the fast radio bursts, sudden, millisecond-long eruptions of energy detected by radio telescopes in the past decade. Some repeat. Some come from galaxies billions of light-years away. Magnetars have been implicated as possible culprits, their magnetic quakes producing bursts that race across the cosmos like cosmic thunder. These are not quiet corpses. They're stars screaming in a language humanity is only beginning to decipher. 2. Watch the echo of collapse is to be reminded that the universe resists closure. Instruments like NASA's Chandra X-ray Observatory, ESAS-XMM Newton, and the James Webb Space Telescope turn their lenses toward these remnants. And what they find is persistence patterns of longevity that challenge every neat diagram in astrophysical textbooks. A white dwarf glowing like a cooling diamond, pulsar beating like a heart that refuses to stop. A magnetar tearing itself apart with invisible violence. And in each of these, there lies a question. What is the true nature of death in the cosmos? Perhaps energy is never truly gone, only translated into new forms. Perhaps matter, when compressed to its limits, discovers new laws, new behaviors hidden from the physics of ordinary stars. Or perhaps, in the silence after collapse, the universe allows a glimpse of its deeper architecture processes, rooted not in fusion or thermodynamics, but in the fabric of space-time itself. To observe these echoes is to feel both wonder and unease. For if stars refuse to obey the rules of their deaths, then the universe is not as predictable as once believed. The remnants of collapse linger like ghosts, reminders that endings are rarely absolute. What was supposed to be silence instead becomes signal. What was expected to fade becomes a flare. The cosmos, once thought to move with mechanical certainty, reveals itself to be restless, alive with persistence. The echoes of collapse are not merely scientific anomalies. They are philosophical provocations. They force humanity to ask whether death, in any form, is as final as it appears. For in the vast darkness, where light should have vanished, the remnants of stars continue to glow, to pulse, to erupt silent but not gone. Asterisk. In the chronicles of the universe, every star is expected to keep its appointment with silence. Its light, however brilliant, must someday dim. Its heat, however fierce, must eventually fade. The mathematics of cooling curves were meant to chart these final journeys with precision. Yet across the sky, astronomers began to find stars that would not abide by their timetables. Shadows that should have vanished lingered, glowing faintly, defiantly, as if some unseen hand had delayed the hour of darkness. Neutron stars were among the first rebels. Their life after collapse was supposed to be short-lived, cooling rapidly. In the first million years, slipping toward invisibility. But telescopes revealed something startling. Some remained luminous, far beyond their predicted span. Their X-ray emissions glimmered like coals long after the fire should have gone cold. In some cases, they blazed with thermal radiation millions of years older than their supposed expiration. The equations faltered. Energy was being replenished from somewhere, somehow, as though the very fabric of the star was hiding reservoirs untapped by conventional physics. The phenomena forced astrophysicists to consider the strange physics of matter under crushing density. Superfluid neutrons, exotic particles, or dark matter interactions might provide a secret engine within these remnants. Yet even these speculations seemed incomplete, like sketches drawn against a horizon too vast to comprehend. The stars kept shining. Their persistence a quiet rebellion against the laws of thermodynamics. Then came discoveries more dramatic still. In the early 2000s, astronomers began to witness a phenomenon that seemed almost paradoxical. Stars that exploded but did not die. These became known as zombie stars. In galaxies far beyond the Milky Way, telescopes recorded supernova-blazing detonations bright enough to outshine entire galaxies. Yet when the light of the explosion faded, the parent star remained, battered but alive. Against expectation, it had survived its own death throes. One such case unfolded in 2012, when astronomers observed a colossal stellar outburst that resembled a supernova. For months, its brightness dazzled the cosmos, a beacon of destruction visible across intergalactic distances. Yet years later, when researchers trained the Hubble Space Telescope back upon the same coordinates, the star was still there, scarred, but unextinguished. It had endured the very event meant to annihilate it. Such stars seem to possess a resilience beyond the imagination of astrophysics, as though collapse itself could be resisted, reversed, or suspended. Supernova imposters deepened the mystery further. These eruptions mimicked the grandeur of stellar death, with plumes of gas hurled outward and luminosities rivaling true supernova. But they lacked the terminal conclusion. Instead of obliteration, the star survived, its core intact, as if mocking the inevitability of destruction. These imposters, often linked to massive stars shedding enormous amounts of matter, blurred the boundary between life and death. A star might appear to die, only to stagger back into persistence, dimmed but not destroyed. The deeper riddle emerged. Was death itself negotiable in the cosmos? Could it be delayed, resisted, perhaps even undone? If the death of stars was not always final, then what other endings in the universe might prove to be illusions? Some theorists suggested that binary companions could rejuvenate a failing star, feeding it streams of matter that reignited its furnace. Others posited that massive outbursts were a kind of purging, a violent shedding of instability that allowed the core to continue burning. Yet neither explanation could fully tame the enigma. The universe, it seemed, had woven ambiguity into the very process of stellar mortality. To witness such defiance is to feel both awe and unease. For if stars bound by gravity and nuclear physics can resist their appointed end, then the cosmos is more flexible than theory admits. The distinction between life and death, between persistence and disappearance, grows blurred. These undead stars, luminous long after their expected silence, challenge not only astrophysics but philosophy. They remind humanity that permanence and impermanence are not opposites, but intertwined threads in a cosmic fabric still being woven. The shadows of collapse are not vanishing as they should. They stretch across time, luminous and lingering, whispering that the universe does not close its books so easily. It delays, it revises, it deceives. And in those shadows lies a question both haunting and profound, perhaps in the cosmos. Death in existence itself. Death is never final, but merely another transformation, waiting to be understood. Every unanswered question in astronomy invites a chorus of theories, and when stars themselves refuse to follow the script of death, the chorus grows louder, tangled, speculative. Reaching beyond the boundaries of known physics, the shadows of collapse that linger in the sky are not simply curiosities. They are challenges to the very framework of science. To explain their defiance, researchers turn to matter, energy, and space-time itself, weaving together a web of possibilities as vast and fragile as the cosmos it seeks to describe. At the heart of this web lies the mystery of neutron stars. These are objects so dense that a single teaspoon would outweigh mountains, so compressed that ordinary atoms cannot survive. Protons and electrons are forced together, leaving behind seas of neutrons pressed into a quantum fluid. But many suspect this is only the surface of their strangeness. Deep within their cores, conditions may be so extreme that neutrons themselves dissolve into their constituent quarks, creating a quark-gluon plasma state of matter that last existed in the first moments after the Big Bang. In such a heart, matter no longer behaves like matter at all. Instead, it flows as a soup of fundamental particles, bound by the strong nuclear force, leaking energy in ways unknown to classical physics. Could such exotic interiors explain why neutron stars shine long after they should have cooled? Perhaps collapse does not end with silence, but with a rebirth into new states of existence, invisible to human senses yet potent enough to alter the march of time. Others imagine hyperdense particles stranger than neutrons, containing heavier quarks, lurking inside these stellar corpses. Hyperons, if stable within the crushing density of a neutron star, would dramatically alter its structure and energy. Some theorists extend the speculation further to strange matter, a hypothetical state where up, down, and strange quarks form an exotic fluid more stable than any known matter. If strange matter exists, it could convert entire neutron stars into strange stars, radiating heat and light in ways wholly alien to standard models. What appears as persistence may not be defiance at all, but a transformation into something. New stars reborn into identities unknown, yet exotic matter is only one strand in the web. Another lies in the invisible fabric of the universe, dark matter. Though it outweighs ordinary matter 5-1, its nature remains elusive, detectable only through gravity. But some theorists believe dark matter may do more than shape galaxies. It may seep into the cores of stars, interacting faintly with their particles, releasing hidden energy that slows their cooling. Among the candidates is the axion, a hypothetical particle born from attempts to solve unsolved puzzles in quantum mechanics. If ixions exist, they could stream from stellar interiors, carrying energy or perhaps even feeding back into the stars. Processes. A white dwarf glowing too long, a neutron star hotter than it should be, these might not be anomalies, but signatures of dark matter's unseen hand. Quantum fields themselves may also play a role. The vacuum of space is not truly empty, but seethes with fluctuations, particles appearing and vanishing in silence. Some physicists propose that collapsed stars, compressed into extremes, might tap into this quantum sea, drawing energy from the fabric of reality itself. If so, then the persistence of dead stars is not a violation of physics, but a revelation that the universe has reservoirs of energy waiting in its foundation, revealed only in the densest graves of suns, but not All theories reach into the exotic. Some are born from the intimate dance of stars. Binary systems are common in the cosmos, pairs of stars bound by gravity in ceaseless orbit. In such systems, when one star collapses, it may not truly be alone. Its companion can spill matter onto its surface, feeding it like fuel, reigniting processes long thought finished. These stellar cannibalisms can produce novae, bursts of renewed brightness, or sustain a white dwarf far beyond its natural decline. In this way, the silence of death is interrupted not by hidden physics but by the gift or theft of life from a neighbor. Even in the cosmos, survival may come at the cost of another. Yet even these explanations, elegant though they may be, reveal deeper tensions. For every proposed mechanism, there is an observation that resists it. A neutron star too hot for dark matter alone. A white dwarf too faint to be explained by binary feeding. A magnetar so violent its field defies known limits. Each new observation twists the web tighter, forcing theories to overlap, to collide, to fracture. And beneath it all lies the oldest tension in modern science: Einstein's relativity against the strange. Laws of quantum mechanics. Relativity describes the large, the cosmic, the curved fabric of space-time under the weight of gravity. Quantum theory describes the small, the probabilistic, the jitter of particles and fields. Both work with unmatched accuracy in their domains. Yet in the dense corpses of stars, the two collide. Neutron stars and black holes are arenas where gravity crushes matter into quantum states, where equations break, where certainty dissolves. To describe these remnants fully is to ask for a unified theory of nature, something that has eluded science for more than a century. The persistence of dead stars is not just a curiosity, is a reminder of this fracture at the heart of physics. Some go further still, imagining remnants stranger than neutron stars, or even black holes. What lies beyond collapse? Could the universe permit objects made not of matter, but of space-time itself? Some have speculated about gravastars, where quantum vacuum energy holds a star against collapse, mimicking the gravity of a black hole without the singularity. Others propose boson stars, made of hypothetical particles that condense into macroscopic quantum states. These exotic possibilities might survive in silence, emitting signals mistaken for ordinary remnants. In this vision, what astronomers see as defiant neutron stars or cooling white dwarfs may, in some cases, be altogether different creatures, evidence of structures that lie beyond imagination. In this web of theories, none is yet final. Each is provisional, tested against data, stretched to breaking by observation. The stars themselves are the arbiters, their whispers carrying hints of truth across light years. Perhaps the answer lies in quarks, or in ixions, or in the gift of matter from a binary companion. Perhaps the answer is something not yet spoken, a law of nature hidden in the silence of collapsed suns. But the web itself tells a story. It is the story of science reaching into the unknown, of human minds straining to reconcile contradictions, of equations written in chalk and then erased by the stars themselves. It is the story of humility, of realizing that the cosmos is not bound by the simplicity of theory, but by its own restless, elusive logic. The persistence of dead stars is more than a puzzle. It is an invitation. It invites science to look deeper, to risk new ideas, to imagine matter and energy in forms never before conceived. It invites philosophy to reconsider the meaning of death, to ask whether endings exist at all in a universe where even collapse can echo. And it invites humanity to wonder, if the stars themselves cannot truly die, what does that say about the nature of reality itself? The universe speaks in silence, but silence is not absence. It is a language written in wavelengths, too faint for human eyes, in vibrations too subtle for human ears, in particles too elusive for human hands. To listen to the dying stars that refuse their end, humanity has built instruments that stretch its senses far beyond the limits of flesh machines of glass, steel, and mathematics that open the cosmos one spectrum at a time. Orbiting high above Earth, the Hubble Space Telescope, has peered into the hearts of supernova remnants, resolving the filaments of gas that mark the death of stars. Its mirror has captured the faint glow of white dwarfs billions of years old. Their light stretched thin across time, their survival a quiet contradiction to every cooling curve. Yet even Hubble's vision was only a beginning. The Chandra X-ray Observatory, launched in 1999, opened a window into violence invisible to ordinary eyes. In X-ray light, neutron stars blazed like embers, their heat far greater than expected. Chandra traced the magnetic fury of magnetars, recording bursts of energy powerful enough to shake detectors from across the galaxy. It revealed neutron star binaries devouring their companions, flaring with a hunger that made even death unstable. These corpses, stripped to their essence, shone with fire invisible to any earlier generation of astronomers. And now, the James Webb Space Telescope continues this lineage, its golden mirrors tuned to infrared light. Webb reaches into dust-shrouded remnants, piercing the cocoons of matter left behind by supernova. It has glimpsed the cooling atmospheres of white dwarfs, where crystallization turns stellar hearts into diamonds larger than worlds. It measures the faint afterglow of collapse, catching whispers that might otherwise vanish. With Webb, the universe reveals that death is never a clean ending, but a long negotiation between silence and persistence. Yet light alone cannot tell the story. Gravity itself has become a messenger. In 2015, the Laser Interferometer Gravitational Wave Observatorial IGO detected the first ripples in space-time. Waves stirred by colliding black holes. But it was in 2017 that LIGO, joined by Virgo in Europe, recorded the merger of two neutron stars. In those seconds, a billion years of travel collapsed into trembling beams of light across the Earth. The event produced both gravitational waves and electromagnetic signals, a cosmic duet that revealed the forging of gold, platinum, and the heaviest elements of creation. It was not simply the death of stars, but their transformation into the very building blocks of planets and people. These collisions showed that remnants could not only linger, they could meet, merge, and create anew. The search grows wider still. In Japan, Kagra, buried deep beneath mountains, now listens with its cryogenic detectors cooled close to absolute zero, hoping to catch the faintest tremors of collapsed stars. Together, these instruments turn the Earth into a vast ear, pressed against the fabric of the cosmos, listening for the footsteps of dying suns. But the future reaches further. Planned missions like the Square Kilometre Array, a continent-sized radio telescope under construction in Australia and South Africa, will chart pulsars with unmatched precision, measuring their spins and signals to test the laws of physics at their breaking points. Other proposals, such as the Einstein Telescope in Europe or the Cosmic Explorer in the United States, promise gravitational wave detectors so sensitive they could capture whispers from the first stars that ever collapsed, echoes older than galaxies themselves. These instruments are not merely machines, they are promises. Blueprints for humanity's determination to confront the mysteries of stellar death, even on Earth. Particle accelerators attempt to recreate the unimaginable. At CERN's Large Hadron Collider, protons are smashed together at energies that mimic the dense conditions of neutron star interiors. In these collisions, quark-gluon plasma emerges, a fleeting state of matter that may mirror the hidden cores of collapsed suns. In laboratories across the world, physicists attempt to calculate what cannot be seen, running simulations of matter compressed to extremes, testing whether exotic states hyperones, strange matter, or superconducting fluids could explain the refusal of stars to fade. In sterile chambers of steel and vacuum, humanity builds echoes of stellar hearts, searching for answers to the riddles written in light years. And still, the most important work remains the slowest: the patient charting of a star's last embers. For decades, astronomers returned to the same coordinates, measuring faint changes, watching as light diminishes or flares unexpectedly or lingers beyond prediction. A single data point means little. Decades of vigilance reveal patterns: the persistence of white dwarfs, the irregular cooling of neutron stars, the unpredictable violence of magnetars all emerge, not in the brilliance of discovery, but in the steady discipline of time. Science listens to the universe as one might listen to an ancient clock, waiting for the ticks that do not come, the silences that refuse to arrive. Each of these instruments, telescopes, detectors, accelerators, is more than technology. They are extensions of human wonder, born from the refusal to accept silence as final. They stretch humanity's reach into domains where eyes cannot see, ears cannot hear, and hands cannot touch. They are acts of defiance, as much as the stars themselves, against the inevitability of ignorance. Through them, the dead stars reveal their secrets slowly. They shine when they should be dark. They collapse and yet survive. They die but linger, whispering across the void. In each instrument, from orbiting mirrors to subterranean lasers, is a witness to that paradox, a reminder that the universe is not a machine of neat endings, but a restless symphony still unfolding in the patient gaze of these machines. Humanity confronts the truth. Death in the cosmos is never absolute. It is a spectrum, a negotiation, a silence that still carries echoes. And with every observation, with every signal caught across the void, those echoes grow louder, drawing science closer to the heart of the mystery, the stars that refuse to die. In the theater of the night sky, death is never fully silent. Even in the ruins of collapse, a star continues to murmur, faint light drifting through the dark, pulses echoing across the void, sudden bursts of fury long after its fuel has vanished. To watch these remnants is to witness defiance, not only of matter against decay, but of the universe against its own prescriptions. The stars that refuse to die are not anomalies in the margins of astrophysics. Etched into the heavens, a star's refusal to vanish mirrors the oldest instinct of life itself, the defiance of inevitability. Across Earth's history, every creature, every civilization has faced the same certainty of ending. And yet, there has always been resistance through memory, through legacy, through the enduring mark of existence on what follows, just as a white dwarf glows faintly for billions of years beyond its final fusion. So do human actions linger after the lives that created them? Silence of the cosmos is immense, but persistence always leaves a trace. This paradox, the coexistence of silence and endurance, forces a deeper reflection. If nature itself resists its own rules, what does that say about finality? Thermodynamics demands entropy. Fusion demands exhaustion. Gravity demands collapse. And yet, dead stars keep their embers, their pulses, their sudden cries. Perhaps finality is an illusion born of limited perspective. To one scale, a star dies. To another, it continues, transformed, translated, but never erased. The persistence of stellar remnants also raises questions about time. A human life is a fleeting breath against cosmic scales, but even the universe itself may not escape impermanence. Galaxies fade, black holes evaporate, particles decay. And yet within this grand impermanence, there is fragility in declaring anything truly gone. A neutron star that should be cold still radiates heat. A white dwarf expected to darken still gleams a magnetar, cracks open with violence long after collapse. What appears to be an ending is only another chapter in a continuum that refuses conclusion. Perhaps this is the deeper lesson. Nothing in the universe is ever truly lost. Energy is translated. Matter is transformed. Memory, encoded in light, travels endlessly through space, bearing witness long after the source is changed. To gaze at a star is to look into the past, to receive photons launched before human existence, before Earth itself was whole. Even in silence, the cosmos preserves its traces, carrying forward the imprint of what once was. The refusal of stars to vanish invites humanity to consider immortality in the naive sense of eternal life, but in the deeper sense of persistence. Immortality may be written not in defiance of change, but in the inevitability of transformation. Just as collapse becomes neutron star, and neutron star becomes pulsar, pulsar becomes silence that still whispers, so too does existence ripple onward, never fixed, never erased. Einstein once wrote that energy cannot be destroyed, only transformed. Hawking showed that even black holes, the most final of cosmic prisons, release radiation, returning matter to the universe. In these revelations lies a truth that transcends physics. Endings are illusions. What appears to vanish is always translated, folded into the wider weave of reality. The stars that resist death thus stand as cosmic mirrors. They remind humanity that mortality is not absolute, but contextual. Each person ends, but their actions ripple. Each civilization falls, but its echoes linger in stone, in language, in memory. The universe itself may one day dim, but not into nothingness, into some new state. It's unimaginable but inevitable, a silence that still carries the memory of its song, and yet the silence remains daunting. The cosmos is vast, indifferent, cold. Stars may refuse to die, but they do not comfort, they do not notice. Their persistence is not for humanity's sake. It is the unfolding of physics, the restless logic of matter under strain. The meaning lies not in their intention, but in humanity's interpretation. To stand beneath their light is to see not only science, but philosophy, an invitation to ask what defiance means in the face of inevitability. If stars resist their endings, then perhaps resistance is itself a fundamental principle. Perhaps the universe is not built on finality, but on continuity. Perhaps immortality is not a gift or a curse, but the natural state of matter and energy, endlessly reshaped, endlessly persistent. The closing image is simple: humanity gazing upward, staring at a star that should be gone but remains silent yet luminous, patient yet defiant. In that light is a question as old as thought itself. Is immortality woven into the bones of reality? If even the stars cannot truly die, then perhaps death is never an end, but only a passage into silence that still speaks.